And hello, welcome back to our turbulence modeling discussion. So in the last video, we were saying that this was the equation we derived from the energy equation using the first law, but I kind of skipped a lot of steps because I assume we are quite familiar with it already. I just want to make a correction. The final equation here actually applies for ideal gas. Okay, so this is actually for ideal gas. Okay, for ideal gas. Okay, the real one, I think the full equation will be, general one is like so. It will have the beta t in front, and that is what it should look like. That is what it should look like. Beta t here, and if for incompressible fluid, we will get this kind of a relation. Alright, you get this kind of correlation. This whole thing disappears. Right, so I mean, to start, we could of course do for ideal gases or compressible fluids in general, but to keep things simple, we will just use the incompressible ones. Okay, we do incompressible for assumption for simplicity's sake. All right, so I mean, to obtain our turbulence relations, we'll need to do the averaging again for the Reynolds average Navier-Stokes kind of a formulation. So this is not Navier-Stokes, this is the energy equation, but we still have to decompose everything into T and T prime, what have you. Okay. And also for simplicity's sake, I mean, to do this derivation, we can also assume K and Cp don't change much. Okay, we can assume they don't change much. Of course, in reality, they will change with temperature, but for the sake of simplicity, we want to combine them into the thermal diffusivity kind of way. Then yeah, I want to get rid of this complexity, right? So recall alpha equals to K divided by rho Cp. Okay, so this measures, I think, on the whole how quickly the temperature gradients actually can, or the temperature differentials actually propagate through the medium. Okay, so we can actually divide throughout by rho Cp, and then we will get here, we can put alpha in here. Okay, and this one you can divide it over rho Cp here, and likewise for the last term as well. All right, again, for simplicity, I will ignore these two terms. Okay, I don't assume heat generation in here, so that's what I'm gonna do. Okay, first thing first, this thing, yeah, this is kind of gotten rid of for simplicity. This one, I would say, for most cases, except in like lubrication or oil flow in pipes, this can be, or crude oil flow in pipes. This was from Bejan. Say, except in flows, such flows, lubrication and flow of a viscous fluid, for example, of crude oil in the pipeline, this dissipation term is usually negligible. So again, we want to make it simple as possible, just for the sake of understanding, not for the sake of rigor. We can start to attempt finishing up this closure problem. All right, defining our closure problem as we do for all turbulence. So I'll bring this alpha out since it's relatively constant, and this I'll just put it as such, delta t squared, or nabla square t. This is the Laplacian, I think. Yeah, Laplacian term. Then this d by dt I can expand out. Okay, into the following. We know that's partial by partial t, okay, plus u partial u t partial x plus v partial t partial y plus w partial t partial z. Alright, so this is the substantial derivative. Okay, this is a substantial derivative, and next thing we'll need to do is to sort of get ready our averaging. Okay, so we can time average for steady state solution. This is the most simple way of averaging, this for Reynolds average Navier-Stokes. Okay, so this one I'll go through later, the closure model and everything, but let's have a closure problem first. So we'll time average, and this term usually disappears when we just do the time averaging. Alright, because remember, we can actually bring this differential out of the integral when we do time averaging. Time averaging is just like you do integration. So let's get it out there. Okay, and actually this will just reduce to 0 if you consider t over all time. Now that leaves us with this to sort of average. So of course this actually won't be 0. This only is equals to 0 for Reynolds average Navier-Stokes, but this actually will remain. Okay, this will remain for LES. This is the filter process, usually used with spatial averaging. Okay, so we just do a bar over all of them, and we do a bar on the right hand side. Again, with the Laplacian term, this right hand side term we can just get rid of. We can just take these two out, no problem, and we can individually do filtering over each of these individual terms. Okay, can do filtering over these individual terms, so let's try that. Okay, 1 plus, okay, let's get this out here. That was a bit of a waste. Alright, let me do this here. Alright, that's 1. Okay, that didn't go the way I wanted, but okay. So this is 2. 1 here, 1 here, and this is 3, and I'll cancel this out. Okay, so this thing has to be, you know, time averaged. All right, so the filter, I mean, we do this definition, right? The filtered version of this, or rather, the average version of this, I don't do filtering yet, is equals to integrate from 0 to infinity. Okay, this is time averaging, yeah? Time averaging. So of this, okay, dt, okay, 1 over delta t. All right, or rather you can do over this delta t. All right. 0 to delta t, or whichever time interval you use. Usually delta t goes to infinity. Okay, so that's usually the case. So let's take out that for purposes. All right, so how do we integrate this thing? All right, to do this we can consider this following thing. Okay, we have partial by partial x of u times t equals to, okay, u partial t partial x plus, okay, oops, sorry, my bad. I should not be doing this. What I should do instead is to start decomposing this into the correct terms. So this u, I need to decompose it into u bar plus u prime. Likewise, t bar will do the same. T equals to t bar plus t prime. Alright, I need to do that first. So once I do that, it should be a little bit easier to see how this whole thing goes. Alright, so I will start to expand this out. Okay, first thing, so yes, we do have a u bar dt bar dx. Okay, that's first, plus u bar dt prime. There's a dt prime dx. Okay, so that's the u term taken care of. And then I will have the same except with u prime. Okay, I hope didn't make any careless mistake here. Alright, looks okay. Okay, so we have this kind of correlation here, but okay, maybe it's not so helpful. Sorry, I think there was a better way to do it. A mistake, but yeah, let's do the better way, the easier way. All right, I'll just take this equation here. All right, and I'll try to have it in the form of this. Okay, we want to bring the differentials inside, or the ut vt and wt inside. Why I'm doing it, you'll find out shortly. It'll be a lot easier when we filter the equations or average the equations like so. Okay, so this will be equals to, of course, you will have this bit here. All right, plus this. Okay, now blah of the, or rather let's put it this way, partial u I partial xi. Alright, so this is what we will get. Partial ui partial xi, this is the u du dx dv dy dw dz. This is actually equals to 0. Okay, from continuity equation. From continuity, yeah, then this is the relation we get. It's very similar to this, but this one was actually found out. Yeah, this one was actually how we did it for our Reynolds average Navier-Stokes. So we're just taking inspiration from that. Okay, now we can apply the filter, or we can apply the averaging. So this one's a lot nicer to average because when we, of course, we do it one term at a time. All right, then we try and bring this in, and then we do the same thing. Okay, we do time averaging first. So of course we can do filtering later on, with a very similar procedure. Okay, and then we will try to separate out the terms. So partial by partial x. Okay, this thing we can actually bring outside. This thing we can bring outside. So you just have the ut on the inside. All right, you just have ut on the inside, which we will then separate out. Okay, u plus u bar plus u prime. Okay, and this is t bar plus t prime. Alright, so we'll do the expansion as usual. Okay, so we can just take q from this. Okay, so I'll just take q from this. What I'll just do is this, like so. Okay, I'll just delete this. Okay, I'll paste it here. Okay, I'll paste it here. Alright, now we got something going. Yes. Alright, so this thing is actually non-zero, it's constant. So we can bring it out. We can bring it out. So I'll just do it like so. You can bring this out. These two terms actually become zero. They drop to zero in the time averaging procedure. But in the filtering procedure, they do not drop to zero. So I can show you that shortly. So I'll just do this first. So filtering is for LES, time averaging is for RANS. Okay, we take a look, we have something like this, because when you filter this, it will still be the same exact value. Alright, the same exact value. Okay, it will be the same exact value. Then we can bring this out like the following. Then we just assume we know that we can just repeat this for the three coordinates x, y, and z. So I'll do this for the x direction. The y direction is kind of the same. I will just replace this with y, this with v. Okay. And likewise, w direction, z direction. This is the same. Okay, and I can bring the varying terms, these terms, to the other side. Okay, like so. All right, u prime t prime. Oh, this should be a negative. Okay, and v prime t prime. I think I forget one more important point, which is I needed to do this. Forgot to filter them, or forgot to average them. Use the averaging notation. Alright, let me go and average it out. I will just fast forward and average it out so that you don't have to look through it. Okay, so I'll just say I average this, and this, like fast forward. So I'll just average the last two terms, and we should be about done here. Okay, we should be about done here. And this thing can go be by itself, this thing can be by itself. This one I can bring it out. Partial z. Okay, of this. Alright, so that kind of covers it. Then these terms, of course, we can expand them out. And okay, we can expand them out like so. Okay, we can have a t bar, partial u bar, partial x. Alright, or let me put it in Einstein notation, because I don't want to write everything out. Ui, xi. Okay, so that will represent t, del u, del x, del v, del y, del w, del z, the summation of these. Now I have a plus u bar, partial t, partial x, plus w bar, partial T bar partial Y plus, okay, this is a V, not W. W bar is the last one. Partial T bar partial Z. Okay, so this is the RANS formulation. This thing actually reduces to 0 from our continuity equation, because I think I covered it in the earlier equations. If we did the continuity equation and we did a time averaging of that, we find that this time average velocity fields, they should have there should be no accumulation of volume in a time average sense, or in the DNS sense, or means to say the instantaneous velocity. It should not be accumulating volume, or it should not be accumulating any kind of mass inside any control volume, whether it be in a time average sense or in the instantaneous sense. So this actually drops to 0. Okay, mass conservation in time average sense. Okay, so this is all that it is. So I can just simplify the right hand side like so for incompressible equation, and that's where we get our closure problem. Okay, so just like before, we'll need to define the following. Okay, 1, 2, and 3. Okay, so this is the Reynolds average Navier-Stokes time averaging, and this is where we get our closure terms from. Of course, the rest of the production terms we neglect because they're not covered in this turbulence theory. But we want to cover this heat transport, for Reynolds average Navier-Stokes, the turbulence theory of it. Okay, so that's all for now. I want to continue in the next video. Thanks for watching. I'll see you guys again.